this lecture we're going to talk about solving a whole class of problems that are kind of Atwood Machines styled problems. And these ones we're going to be dealing with no friction, massless strings and pulleys. We'll get to the point where we'll be able to deal with friction for that block that's resting on the table and a pulley that has mass. But for right now, it's about the simplest problem that we've got. Atwood machines will accelerate because of gravity. So this machine right here, we've got a hanging mass, little m, and you've got a weight acting on little m, and that weight is going to cause acceleration in the system. And we need to be able to deal with these types of systems. All right, so the first technique, the first tip for dealing with these types of systems is you're going to define a positive direction for everything acting, because for the mass resting on the table, I have forces going to the left and to the right, which cause it to accelerate. For the mass that's hanging off the end, I have forces that are going up and down, causing it to accelerate. So we can't just use our standard sign conventions of to the right is positive, to the left is negative, because that will lead to contradictory directions for forces that cause this system to accelerate. So we're going to define one uniform direction of positive acceleration, and in general we're going to say it's the direction of the acceleration of the system. So this system right here is accelerating in this way. The upper box is going to accelerate to the right, and the lower box, the hanging box, is going to accelerate down. So since that's the direction of the acceleration of the system, that is what I'm going to define as the positive direction for this problem. All right? So positive is going to be anything for the box on the table that makes it move to the right, anything for the hanging box that makes it go down. Okay? So drawing in a free body diagram, I've already got the weight of the lower box, and we've got a tension force acting upwards. For the box resting on the table, yes, we have big mg going down, and we do have a normal force acting on that box. Since there's no acceleration in the vertical direction, and since we're ignoring friction, we can safely ignore the vertical forces for this problem. And we have a tension force acting on it to the right. Important to understand that the tension force for the upper box is the same as the tension force for the hanging box, because the string is massless and so is the pulley. If the pulley has mass or the string has mass, then those tensions would not be equal, but for us they are. So now let's talk about the sum of the forces acting on the box that's resting on the table. We've got the sum of the forces acting on big M. He is, we're going to assume, accelerating to the right, so that would be his mass times his acceleration. Which forces are acting on big M horizontally? Only tension. And that is going to the right, so I'm going to leave it positive. That's equal to his mass times his acceleration. And for the box that is hanging, we have the sum of the forces acting on little m is equal to, now here we have to be careful about our directions. I've defined the direction of motion as positive, so in this case mg is going to be positive, tension is going to be negative. Regardless, the sum of the forces acting on little m are going to be his mass times his acceleration. So filling in the forces more fully, we have mg going in the direction of acceleration, so that's positive, and the tension force is going to be negative here. That's equal to little m times a. So things that we can solve for. First off, what's most important in most people's minds is going to be the acceleration of the system. So we want to solve for a, which means we need to get rid of t. Well, we already have an equation that's solved for t in terms of big M and a. So we can go ahead and plug that in all the way over here for t. So let's go ahead and do that. We end up with mg minus big M a is equal to little m a. We're solving for acceleration here, so let's get acceleration together on the same side. So we've got mg is equal to little m a plus big M times a. Factoring out an a, we have mg is equal to a times little m plus big M. And solving for a now, and let's go ahead and put this over here, we have the acceleration is equal to little mg divided by the total mass of the system. So here then is our expression for the acceleration of the system. It's equal to the force that's causing the acceleration. That's the little mg, the weight of the hanging box, divided by the total mass of the system. All right? So that's really important, that bottom term. We have to divide by the total mass of the system, big M plus little m. And now we can solve for the tension. On either side, we've got tension is equal to big M times A on this side, so that's the easiest equation to deal with. Let's go ahead and plug A back in. So we get tension is equal to big M times little mg over little m plus big M. And a quick look at our units in this final equation that we get. We've got kilograms times meters per second squared on top. We're dividing that by kilograms on the bottom, so kilograms cancel out, but then that whole thing is multiplied times kilograms. Kilograms times meters per second squared is a Newton, and the unit for tension, since it's a force, should be newtons. And there it is. If we had numbers, we'd plug them in. We'd find the tension in the string, we'd find the acceleration of the system. So the key to understanding these types of problems is setting up which direction is going to be positive. Always make the direction that the system accelerates in as the positive direction for both objects, or all three objects. Draw your free body diagrams for both objects. Talk about the sum of the forces acting on both objects. Fill in your equations, solve for the unknowns. As you can see here, we had two equations, two unknowns. Our unknowns were tension and acceleration. So I have one equation on the left that have tension acceleration. I have another equation on the right with tension and acceleration. And I used two equations to solve for those two unknowns. Other types of Atwood systems, the most common you'll see is you've got a pulley here, and on one side is a little m, and on the other side is a much larger m. Find the acceleration of the system. These problems work the same way that we just saw. You're going to define a positive motion or a positive direction for both masses. You're going to draw a free body diagram. Here we've got little mg going down, and we've got the tensional force going up. And on this side we have big mg, and the tensional force going up. And this mass on the left-hand side accelerates in the positive direction, as we've defined it, because the tensional force is bigger than mg. This mass on the other side, on the right-hand side, accelerates downward, which is still the positive direction for it, because the weight force is bigger than tension. And we're going to solve this the same way. Talk about the sum of the forces acting on little m, the sum of the forces acting on big M. You again are going to have two equations, two unknowns. Your unknowns are still tension and acceleration. Solve for the acceleration in the system. We can do all sorts of fun stuff once we know the acceleration. Say the ground is down here and big M starts a certain distance y above the ground. How long does it take for the system to stop accelerating, for big M to hit the ground? All right? So define your positive direction of motion for the system. Draw your free body diagram. Talk about the sum of the forces, Newton's second law, for both little m and big M. Solve for your unknowns algebraically. Piece of cake. Talk to you later.